Hi everyone. Today we'll be talking about integration by parts. Now, what is integration by parts? Integration by parts is effectively a way of reversing product rule. Okay, so although we don't have a exact trick or exact rule for just integrating the product of two functions, what we can do is we can rearrange what we know from product rule to give us another form of integrating whatever's in that integrand. Okay, and it doesn't make as much sense just yet, but what I've written here is product rule, and then I'm going to just show how we can derive integration by parts, the integration by parts formula from this. So we're going to start off with product rule, and it says if you have the derivative with respect to x of u times v, where u and v are both functions of x, so you could even have it as like u of x and v of x, then it's going to equal v times u dash plus u times v dash. So yeah, okay, sick. Now, to get our integration by parts formula, I'm going to take the integral of both sides with respect to x. Now, of course, if I take the integral of this side with respect to x, I can then go and split up that integral as the integral of this one, and then plus the integral of that one, which is what I will do. Okay. Now, I'm going to take this and subtract the v u dash dx from both sides. And what are we going to get? Well, in our next line, we'll write it in black. We're going to get the integral of d dx of u v with respect to x minus the integral of v u dash with respect to x equals, and then the integral of u v dash with respect to x. Okay, I'm just going to rearrange this so I have this on the right hand side and this on the left hand side. And as I do that, I'm just going to see what this is. So as you can see, derivative of u times v, and then you're then taking dx, or then you're integrating with respect to x, these things effectively cancel each other off, and you're just left with u times v. So that means if you have the integral of u v dash dx, it's going to equal uv minus the integral of v u dash with respect to x. Perfect. This thing here is integration by parts. It basically states that if you're trying to find the integral of a product of two functions, treat one of them as if it was the derivative of some other function, okay? And then it would equal uv minus, and then find that some other function, which is effectively the integral of that b dash, and then multiply by the derivative of u. Now this sounds a bit weird, so I think a few examples probably makes a bit more sense. Okay, let's take a fairly simple example, I reckon, to start off with. Let's start with the integral of x e to the x dx. Okay, as you can see, this here is made up of two functions, the x and then the e to the x, and there's no real way to integrate this unless we have some form of like a reverse product rule, okay, i.e. integration by parts. Because we've come to this identity, what we want to do is we want to get our integral to look like this left-hand side, okay? So to get it to look like that left-hand side, I have to choose, should I make this my u and that my v dash? Or should I make it the other way around and make that my v dash and that my u? Because if I can choose which one's my u and which one's my v dash, I can then just go and sort of evaluate the left-hand side of the right-hand side of my rule, okay? I'm going to first do, I'm going to choose where the x is the v dash and the e to the x is the u. Well, in order to fill everything in on my right-hand side, if I know what u is and I know what v dash is, I have to find what v is and I have to find what u dash is. So I'm going to say, well, okay, well, if u equals e to the x, that means u dash is equal to e to the x. And then if I make v dash equal to x, to find v, I just have to integrate it, which means v is simply just going to be a half of x squared. Now, if I go and apply that rule, let me see if it's going to help me evaluate this integral. So the rule says u times v, which means it's e to the x times a half of x squared. So that's going to be a half of x squared e to the x. Actually, let me put this all in red. And then minus the integral of vu dash. So that is a half of x squared times e to the x dx. I think you can tell here that this is fine, whatever, we have that integral. But then I have to somehow go and integrate this, which is not any easier than having to integrate this in the first place. Because again, you have the product of two functions and you can't really do u sub for this. And you can't do reverse chain rule because it's not like you have the derivative of this particularly present day. You still have this x squared. You're kind of stuck. So I think in this case, we made the wrong choice of v dash and u. But what if I swap it around? What if I take this same example, but instead of making u equal to e to the x, I make u equal to x, and instead of making v dash equal to the x, I'll make the e to the x equal to the v dash. So let's make this, let's write it in purple actually, it's just a different color. Purple. Let's make that the u, and let's make that the v dash. So again, we need to find the other ones. We need to find u dash. So if u equals x, u dash equals just 1. And then v dash equals e to the x. That means v just equals, well, the integral of e to the x is just e to the x. Perfect. So now if we go back to our rule, we can say that this thing here should equal u times v, so x times e to the x, minus the integral of v u dash. So v is e to the x, u dash is just 1. Perfect. Now, can we actually evaluate this integral? Yeah, we can, because e to the x times 1 is just e to the x. I can easily integrate that. And the integral, of course, just goes to e to the x, and then, of course, plus c. So integration by parts takes product rule, rearranges it, and says, if we can write the integral in terms of a u and a v dash, so something that we are going to differentiate, because we need to find u dash, and something that we wish to integrate, and we can fit it into that form, and the integral comes out kind of nice, then we can find the integral, okay? The idea is you wish to differentiate something out. That is, you would differentiate this x so that in the next integral, it's just the 1 or it's just a constant. And it's easy to integrate this. That's why it actually stays the same, which is perfect. Okay. As you go through these questions, you might find it hard to choose which one is going to be the u and which one is going to be the v dash. But I think you're going to start recognizing some properties. Most of the time, not always, most of the time, you're going to be differentiating out the polynomial. Or, in other words, you're going to be letting u equal to the polynomial function in it. The reason is because if you keep differentiating these polynomials, you're going to get to constants, aren't you? And sometimes it's going to have multiple applications of integration by parts, but whatever, we'll get to that in a moment. But most of the time, your best bet is differentiating out the differentiating out the polynomial, okay? And integrating things like exponentials is quite easy. So that's why. Perfect. All right, let's do another example. So let's find the integral of x plus 1 sine x. Yeah. Okay. As you can see, it's the product of two functions. I can't really do u sub. I can't really do, I mean, definitely I can't do reverse chain rule. So there's no other ways we know how to do this yet. And then we have to do integration by parts. Okay, I said before, it's always good to let u equal to the polynomial. And you can see that here, I should be letting u equal to the x plus 1 and v dash equaling the sine x. Okay? So u equals x plus 1. If I remember, my formula is u times v minus the integral of v u dash. So if u equals x plus 1, I need to find u dash. Now the derivative of that is just 1. And then if v dash equals sine x, well then what's the integral of sine x? Well, sine x comes from minus cos x. Perfect. So now we can say this just equals uv, so that is x plus 1 times minus cos x, then minus the integral of v u dash. So u dash is just 1, which is perfect. It's going to be minus cos x times 1 dx. Wonderful, wonderful. We get this. Now, this is quite easy to integrate. That 1 kind of, there's no need for it. This negative just comes out to there. So in other words, we get minus x plus 1 cos x plus the integral of cos x dx. And what's the integral of cosine? It's just sine. And then plus sine x plus c. Perfect. And then you're done. Okay. I'm going to show you why it wouldn't work if you did it the other way around. I think you can probably see why it's not working, why it's not going to work. Because if this was my v dash, I would have had to integrate it. If I integrate that, that's going to be x squared over 2 plus x, which means you're going to be minusing and you're going to have this x squared over 2 plus x times by the derivative of sine, which is cosine, and it's not going to help. Okay, like that sine cosine will never kind of get differentiated out no matter how many times you differentiate it. But these polynomials eventually just turn to constants, and then you no longer have product of two functions. You kind of just have a constant times some function. Okay, actually, I'm not going to bother doing it. How about if we had the exact same question, but we had it with limits? So the integral from 0 to pi of x plus 1 sine x dx. How do we deal with limits in our integration by parts? Well, it's the same thing, actually. You're going to let this equal to u. You're going to let this equal to v dash. You always have to quote the formula. But because now we're doing, we have bounds, what you're going to say is that it's going to equal u, v, but between your bounds, so between 0 and pi, minus the integral from 0 to pi of v u dash and dx. Okay. You can, if you really want to, find the full integral. That is, don't put any of the bounds just yet. Find the full integral, do all of this or whatever without the bounds. And then at the very end, put a square brackets around it and put 0 to pi. But I find it's better to split it up like this. In fact, this is kind of how it's taught everywhere, because it keeps it clean. Sometimes if you're doing all of the integration and then you want to sub in, it's going to get very long and very ugly. But if you sub in as you go, so in the next line, you would actually sub in the pi and then you'd minus when you sub in the 0. As you go to evaluate this, oftentimes this just goes to 0 anyway. So it saves you a fair amount of time. Wonderful. Anyway, again, we'll say u equals x plus 1, which means u dash equals 1. And then v dash equals sine x. And v equals minus cos x. So we come to this, it's going to be u times v, so again minus x plus 1 cos x from 0 to pi, and then minus, and then this is going to be the integral from 0 to pi, that's going to be a plus, and then it's going to be cos x. Okay, this is just because we did it before, so we know. Now, if we sub in pi into the first one, it's going to be minus pi plus 1 cos of pi, and then minus, but then you have another minus, so plus, and then you have 0 plus 1 times cos of 0, and then you have plus, and what's the integral of sine of cos x? Sine x, so sine x from 0 to pi. Subbing in, cos of pi is minus 1, so we end up with pi plus 1. And then cos of 0 is just 1, so it's plus another 1. And then plus, and then sine of pi minus sine of 0. I think those just both go to 0, don't they? So I think you end up with just pi plus 2. Very nice, very nice, very nice. Okay, what if you had a question like x squared e to the x? Well, e to the minus x. Let's fix this up. dx. Just like before, you're not going to let the polynomial be the v dash. You're going to make this the u because you want to differentiate this. If you keep integrating this, if you make this the v dash and then you have to integrate it, you're going to get a third of x cubed, which is going to make your life harder because you're going to minus and then it's, you know, it's just going to make life hard. Okay, so definitely don't do that. Instead, this is what you want to differentiate, but it might require repeated applications, as you shall see in a moment. Anyway, so you're going to let this equal u, you're going to let this equal v dash. It's also very easy to integrate e to the minus x. So letting u equal x squared, u dash will equal 2x, and then v dash equaling e to the minus x means v equals divide by the derivative of the power, we divide by the minus 1. So we get minus e to the minus x. Wonderful. Always quote your formula, uv minus integral of vu dash. Okay, u times v is going to be minus x squared e to the minus x, then minus, and then I'll show you. So it's going to be vu dash is going to be minus 2x e to the minus x dx. Wonderful. Now, do you see this? I mean, of course, we can take that negative and we can even take that 2 out the front. But then you end up with x e to the x, which is, again, a product of functions. Okay. So it seems like you have to repeat integration by parts again for this thing. So I'll just write this in the next line as minus x squared e to the minus x. Okay. And then plus 2 the integral of x e to the minus x dx. Perfect. Now that we know that, we have to then go and do another application. So another application of int by parts. Perfect. What does it seem like we're going to be letting u equal? If I make v dash equal to this and u equal to this, I'm going to integrate this and I'm going to get back with the x squared. What's the point? Okay. So I'm obviously going to differentiate that and then integrate this, just like what I would, basically like what I did before. So this is the u, this is the v dash. Okay, make sure you don't accidentally look back at your work from before because you have all of the u's and the v dashes there. Okay, so let's write this, x, u dash is 1, v dash is e to the minus x, v equals minus e to the minus x. Wonderful. Now this is minus x squared e to the minus x plus 2. Now that goes to the entire thing. That goes to the uv minus integral of vu dash. That plus 2. Be careful with these pluses and minuses because oftentimes that's where people make the mistakes. You forget to expand the 2 to everything, or you forget that if there was just a minus here and there wasn't a minus there, that minus goes to the entire rest of the integral. Okay. So here we get minus x squared e to the minus x plus 2. And then u times v is minus x e to the minus x minus the integral of vu dash, so minus e to the minus x dx. Okay, you can see with all these negatives, it's very easy to mess up. Make sure you don't. So minus x squared e to the minus x. And let's just, should we just expand and integrate? No, I'll leave like this for now. Okay, what's the integral of this? Well, divide by the derivative of the power, so dividing by -1, you're going to get just minus. That's already from there. And then this is just e to the minus x. So you can put a plus c there. Let's expand. So minus x squared e to the minus x, and then minus 2x e to the minus x, and then minus 2 e to the minus x plus c. Perfect. Okay. Yeah, not bad, I think. I think this is pretty good. Okay. I'm gonna give you another question. I want you to have a go at this on your own. So x ln x dx. Have a go. Try what you think u should equal, what you think v dash should equal. Maybe if you want, attempt both ways. So pause this recording and then come back to me. Okay. Sick. Pause. Okay, now unpause. So you might have recognized, if you did what we did before, that is, you let the polynomial equal u and you let whatever other function equal the v dash, you run into a bit of an issue because you end up with this. U equals x, you can easily find u dash. Then you end up with v dash equaling ln x. And you're like, wait, how do I integrate ln x? In fact, that requires integration by parts. So you haven't really solved it here, have you? Okay. Oftentimes, you're going to be letting the polynomial equal the u because it's easy to differentiate that. But in particular circumstances, it is actually, if you let v dash equal the other function, it's actually quite hard integrating those functions. For example, you might be trying to integrate ln x's. You might be trying to integrate inverse functions like inverse sine, inverse tan, inverse cosine. Okay, those ones you can't really integrate unless you do integration by parts for those. So in that case, it's much easier to differentiate those. And even if it's a polynomial, it's quite easy to integrate a polynomial. Okay. And that's how you do those ones, slash this one as well. So instead, I'm going to swap these around. I'm going to say that this is the v dash and this is the u. And if we come to here, we'll get rid of all of that. U equaling ln x, the derivative is just going to be 1 on x. And then if v dash equals x, the integral equals, add on to the power, divided by the new power, a half of x squared. Again, quote your formula. And let's sub in. So vu, sorry, it's going to be a half of x squared ln x. Then minus, and it's going to be vu dash. So the integral of v, which is a half of x squared, times u dash, which is 1 on x dx. Oh, wow, this is actually pretty easy to integrate because it's just a polynomial there. So this is going to be a half of x squared ln x, then minus a half, we'll put out the front, and then x squared on x is just x dx. Integrating this, we get minus a half. Now, actually, we won't bother writing that in. The integral of x is just a half of x squared. So when you take the half times the half, you get a quarter. And then plus c. Okay? You're more than welcome to integrate this to show that we were right. But that's how you do this. Okay? Can you, using a similar approach, integrate this for me? think about what you will let v dash equal, what you will let u equal. Maybe do it one way, realize it doesn't work, and do the other way. Okay. Perfect. Alrighty, pause. Now that I've assumed you have actually had a go, I shall go over it. So if you let this equal to the v dash, you have to try and integrate it, and it's kind of hard to integrate inverse sine of x. Like, I think that's the next question we'll be doing. Okay, so instead, we have to make this equal to the u. It's quite easy to integrate, differentiate inverse sine of x. And let's make this here equal to the v dash. So if u equals inverse sine of x, what's the derivative? I think we've already spoken about this. So it should be 1 over, and then the square root of 1 minus x squared. Now, if v dash equals x, v should equal a half of x squared. This equals uv minus the integral of vu dash dx. Okay, oh, by the way, this is on your reference sheet, so I guess you don't have to remember it, which is good. U times v is going to be a half of x squared inverse sine of x minus, and then it's going to be the integral of v u dash. So I'll take the half out the front, and then it's x squared on, and then the square root of 1 minus x squared dx. Okay, I like this. This is a juicy question. I really hope that you didn't stop here and you actually had a go at trying to force this to work. Okay, so let me just take this off, maybe a bit closer to here. So it's going to be a half of x squared inverse sine of x. Now, to integrate this, we need a bit of manipulation. What I'm going to do is try and get it so that I just have a constant in my numerator. Maybe that means forcing my numerator to look exactly like my denominator, and doing some special magic with it. We'll talk about that in a minute. So minus a half. What I'm going to do is make that a plus, and then put in here a minus x squared. I'll put the minus in like that. You could have also done some form of u sub with a trig function, but I'll get to that in a moment as well. Actually, should I just do it from here? No, I want to show you how to manipulate this as well. Okay, now I'm going to add 1 and then minus 1. Okay, there's no harm in doing this. And I'm going to split up the integral. But splitting up the integral means they're both multiplied by that half. So it's going to be 1 minus x squared over, and then this is going to be 1 minus x squared. In fact, I actually won't even write it like that. I will write it as to the power of a half, 1 to the power of 1 dx. And then minus, and then it's the integral of 1 over the square root of 1 minus x squared dx. Perfect. So this is going to be a half of x squared inverse sine of x plus, and then if we just, you're dividing, it's the same base. So if you're dividing, you subtract the powers, you end up with the integral of the square root of 1 minus x squared dx, because 1 minus a half is a half. So it's 1 minus x squared to the power of a half. Then minus, and then isn't this the exact standard form for inverse sine of x? Yes. So then that becomes inverse sine of x, like that. I'm just going to expand this out and take this, because it's been already evaluated, I'm just going to bring it to the front. So it's going to be a half of x squared inverse sine of x minus a half of inverse sine of x, and then plus a half of the integral of the square root of 1 minus x squared dx. Perfect. For this, I'm going to use some form of substitution. I think we've already done some examples of this, and because I know that one Pythagorean identity for trig i.e. I know sine squared theta plus cos squared theta equals 1. If I let x equal sine theta, I can see that dx should just equal cosine theta. Dx on d theta, like this. And that means dx equals cos theta d theta. Okay. Wow, I'm writing so small. It's not good. I can now start rearranging everything. So this is all already, I'm just going to copy this so I have to bother rewriting it every time. And plus a half of, and then this integral, when I sub in that value, it's going to be, or that substitution, 1 minus sine squared theta times cos theta d theta. So this is a half, no need. What's that? Plus, and then the square root of 1 minus sine squared, 1 minus sine squared is cos squared, and then square root of that is just cos, but then it's cos times cos, so it's cos squared. Now remember, we have a substitution for cos squared theta. That is, we can write it in terms of cos 2 theta. We can say this is inverse sine of x minus a half inverse sine x again, plus 1 over 2. And then remember, the rule is cos squared theta equals a half of 1 plus cos 2 theta. So that half with that half come together to give you a quarter. And then it is the integral of 1 plus cos 2 theta d theta. Good, good, good. And then the integral of that is theta plus 1 over 2 sine 2 theta. Okay. Now we have to go back to our original. Okay, so if we start off with what we let x equal, we let x equal sine theta. So let me put that here. We let x equal sine theta, which means I need a replacement for this. That's quite easy. It just means theta equals inverse sine of x. I feel like there's a lot of inverse sines of x's here. Who would have thought? Not me. And now, just we need to find a replacement for sine 2 theta. Okay, well, this is quite easy because all I have to do is take this and draw a little bit of a triangle for it. So if that's theta, and it says sine of theta equals x, it's kind of like saying x over 1. That's x there, that's 1. That there's the square root of 1 minus x squared. And that means I can also find cos theta and whatever else I need. Okay, this is pretty easy now because I know my double angle expansion for sine 2 theta. It is 2 sine theta cos theta. Wonderful. So bringing this all together, we have the exact same. We don't want that. You know, I'm just going to write it from here. What is this going to be? That's going to cancel. That's going to cancel. Sine theta is just x, and then cos theta is the square root of 1 minus x squared. So bringing this, we have a half of x squared inverse sine of x minus a half of inverse sine of x, and plus a quarter of inverse sine of x, and then plus a quarter of sine theta is x, and then cos theta is square root of 1 minus x squared, and then plus c. Here we have minus a half plus a quarter of these inverse sines. So this is going to give us there you go. That's actually a good question. I really hope you got to the end of that. I'm a major fan. Okay. Alrighty. I think I said the next question we'll do is the integral of inverse sine of x on its own. You're probably sick of hearing about this, but it's good to do. Okay. Now, why is this integration by parts? There aren't two functions being multiplied together, are there? It just seems like it's inverse sine of x. But I don't know how to integrate this, right? So what's our only other option? Well, what if I write this as 1 times inverse sine of x? Now, 1 is technically a function of x. It's a function of anything, but yeah, it's a function. And then I go and I let u equal the inverse sine of x, and I let v dash equal the 1. Okay, actually, let's make this a definite one. So from 1 to 12. Okay. One of the important rules in integration by parts is sometimes letting v dash equal 1. Okay, especially when it seems like there's just one function on its own which can't be integrated. Okay, letting v dash equal 1 sometimes can get you a better form in that. You know how this equals uv minus vu dash. Sometimes this vu dash becomes very easy to integrate because this gives you an x which might be required, you know. Anyway, you'll see. So if u equals inverse sine of x, u dash equals 1 over, and then the square root of 1 minus x squared. Perfect. V dash equaling 1 means that v just equals x. So bringing this, we have u times v, so we have x inverse sine of x. We have minus, and then we have the integral of v u dash. So that is x over the square root of 1 minus x squared dx. Okay, perfect. I feel like this is just chain rule here, isn't it? Or like reverse chain rule. Because it seems like this is the function and you have the x that's part of the derivative of that function. You just sort of need a minus 2 there. That means you need to make this a plus and then a half. Perfect. So this is x inverse sine of x, and then plus a half, and then that's 1 over the square root of 1 minus x squared. That's like 1 minus x squared to the power of minus a half, which means when you add on to the power, it becomes to the power of positive a half, and then you've got to divide by the derivative of the inside. So dividing by a half is the same as multiplying by 2 and adding c. Okay, that 2 and that thingy cancel, and or did I forget that this was a definite? So that should be like this: 0 to a half, 0 to a half. No need for that plus c, my bad. Okay, well, if we sub in, I think if I remembered, I would have already have evaluated this in this line, considering it was already expanded there, but no, it's fine. So now expanding or subbing in, we get a half inverse sine of a half. Okay, and then we get minus 0 times inverse sine of 0. And then, of course, those would have already cancelled. So we get plus, and then we have the square root of 1 minus, and then it's a half squared, then minus, and then the square root of 1 minus 0 squared. Okay, so when does sine equal a half? It equals half at pi on 6. So this is a half times pi on 6 minus, and then that's just 0, so that goes. And then you have here 1 minus a quarter, which is 3 over 4. So then it becomes plus the square root of 3 over 2, and minus 1. And there we are, pi on 12 plus root 3 over 2 minus 1. 6. Okay, perfect. There you go. I think I'll give you some other examples just for you to work on. Can you find the integral of ln x dx? Maybe using a similar process. I don't know. Okay. So have a go at that. And yeah, once you finish, let me know. Or let me know, what am I talking about? Once you finished, unpause and we can do it. So again, in this case, you can put a 1 there. You don't really have any other choices. And you'll let this equal your v dash, and you'll let this equal your u. So if u equals ln x, u dash equals 1 on x, v dash equals 1, v equals x. Okay, so this together gives you uv minus integral of vu dash. Yeah, of course. So u times v is going to be x ln x minus, and then this is the integral of v x times u dash, like this. Obviously those cancel, you just get 1. And then now to integrate, just becomes like that. Perfect. Okay. Now I want to give you a different type of question. What if we needed to find the integral of e to the x sine x dx? There's no polynomial here which we can choose to sort of differentiate out, right? So if we look back at one of the other examples we did here, it took us two applications of integration by parts to fully differentiate out this polynomial, this x squared, okay? It doesn't seem like that's what's going to happen here, because neither of these are going to get differentiated out to a constant. This is going to remain e to the x. This is going to go through a cycle. It's going to go like sine x, cos x, minus sine x, minus cos x, sine x, and then keep going. Okay, so it just repeats in that 4-function cycle. Okay, but what if we can utilize that cycle? Maybe it might take a few operations or a few applications of integration by parts, but actually, we'll go through the example and you'll see. In this sort of question, doesn't actually really matter which one you let equal the u and which one you let equal the v dash, because both are really easy to integrate as well as to differentiate. So, and you can show this for yourself. I'm just going to let u equal, what should I do? Let u equal this, and let that equal my v dash. Okay, perfect. So if u equals sine x, u dash equals cos x, and if v dash equals e to the x, well, v just equals e to the x. So applying this, we get v u, so e to the x cos x. I need to pause the recording for a moment. Sorry, my dad called, so I had to answer that. Okay, let's keep going. So v u, then minus v u dash, so that's e to the x cos x dx. Now here we have not really gotten anywhere because we have this e to the x cos x that doesn't really simplify or doesn't really integrate easily. So it seems like we have to do integration by parts again. So apply int by parts again. Okay. So u, it doesn't really matter which one we do. So let's just go again. Let's say u equals the cos x, u dash equals minus sine x, and then if v dash equals e to the x, v should just equal e to the x again. So this is going to be e to the x cos x. Remember that minus should go to this entire thing. Be minus like that. And then it's again uv or vu, so that's going to be e to the x. Yeah, hold on. Did I mess up something here? Oh yeah, this here should not be that. I think I did this wrong. It's VU, so that should be sine x like this. My bad. Okay, so then, oh yeah, okay, this makes more sense. So then e to the x, and then you can have a cos x there, and then it's minus, and then it's the integral of, and then it's VU dash, then it's going to be minus e to the x sine x dx. Perfect. And close bracket on that. So now we have e to the sine, e to the x sine x, minus e to the x cos x, and then we have this minus and this minus cancel, but then that means you get a plus, but then you have this minus as well. So then it becomes minus, and then the integral of e to the x sine x dx. Now you might say, well, what do I do now? Because do I just have to keep applying this? I feel like I'm going to go into a bit of a repetition, a bit of a cycle. But if we look to what our original integral that we wanted was, our original integral was e to the x sine x. So let me just write that as the left-hand side of this. We originally wanted to find this, but throughout the integral, we found it showed up on the right-hand side. So I'm just going to move this over to the other side. It's going to become a plus. Then I'm going to have actually two of those integrals. Like this. Now all I need to do is divide by 2. And then I get the integral of e to the x sine x dx equals, I'm going to factor out the e to the x. It's going to be a half of e to the x, and then sine x minus cos x plus c. I hope that makes sense. Yeah, well, that's how you do these things. Okay. Now for extra practice, I'm going to get you to just have a go at some of these integrals. So can you find this? Following. Have a go at that one. Once you have actually, yeah. So have a go at this, and then pause if you'd like. I'm just going to write a few more. How about this? And I'll give you one more. So let's do the integral from 1 to 2 of x squared ln of 2x. Yeah. Okay, so pause, have a go at each of these, and then come back to me once you're ready. So we can do them. Okay, so let us take this first one. Well, this doesn't have any other function, so it probably means we have to use a 1 there. Let's make that my v dash. Let's make this my u. And of course, this is going to be vu minus integral of vu dash dx. Well, if v dash equals 1, v equals x, and if u equals, is that rubbing out? If u equals 10 inverse x, well, we know that the derivative of 10 inverse x is 1 over 1 plus x squared. So this is going to be uv, which is going to be x inverse 10 of x, minus, and then the integral of, and it's vu dash, so it's going to be x over 1 plus x squared dx. And of course, these have bounds, don't they? 0 to 1, 0 to 1. let's solve. So this is going to be 1 tan inverse of 1 minus 0 tan inverse of 0 minus, and then this integral. Well, if you look at this, it almost seems like you have the derivative. So you have this, and then you almost have its derivative on the top. You just need a 2. So I'll chuck a 2.5 there. So we get minus a half, and then that just becomes ln of 1 plus x squared. 0, 1. Do I need the absolutes here, by the way? No, because 1 plus x squared is always greater than 0. So no drama. In fact, actually, I'll just do it now. Convert them to curve brackets. Inverse tan of 1 is pound 4. Inverse tan of 0 times 0, that just goes to 0 anyway. And then we have minus a half, and then we have ln of, what is that, 2? Minus ln of 1. Now, ln of 1 is 0, so this just becomes pound 4 minus a half of ln 2. And you're done. Perfect. Next one. So for this, I let u equal to this, and I let v dash equal to that, okay? Because I want to differentiate out this polynomial. So u equals x, which means u dash equals 1. V dash equals 4 minus x to the power of a half. That means v equals, add 1 to the power becomes 3 over 2, divided by the new power, so 2 over 3, as well as the derivative of the inside, and then 4 minus x to the power of 3 over 2. This is again uv minus integral of v u dash dx. U times v, so minus 2 over 3x, 4 minus x to the power of 3 on 2, minus, put that there, and then the integral of v u dash, so minus 2 over 3, 4 minus x to the power of 3 over 2 dx. Of course, we can take out that minus 2 over 3, can't we? Make it a plus 2 on 3. And then integrating this thingy, we add 1 to the power. So that becomes power of 4, becomes power of 5 over 2. Divide by the new power, so divide by the 5 over 2. And then divide by the derivative of the inside. So then minus 1 and plus c. And we get minus 2x on 3, 4 minus x to the power of 3 over 2, plus minus, rather, 4 over 15, 4 minus x to the power of 5 over 2, plus c. Perfect. Copy this next one. Okay, sine of ln of x dx. So that's again one function. Most likely, I guess actually not most likely, I'm definitely gonna have to put a little 1 there and make that my v dash. Make this here my u. Because there's only one function, and also I can't integrate this. Because if I make this my v dash, then I just go back straight to the question, which doesn't help. So this equals uv minus integral of v u dash dx. U equals sine of ln of x dx, sine of ln of x. U dash equals, well, first the sine goes to cosine of the same argument, then you multiply by the derivative of that argument, so multiplied by 1 on x, and then v dash equals 1, which means v equals x. I think you can see this works out quite well, because then you get x sine ln of x minus the integral of v u dash, that x times the 1 on x cos of ln x. These things sort of cancel off. Okay. Let me get back to this. X minus, and then you get the integral of cos of ln x dx. What do I do here? It seems like I'm stuck. How about I do integration by parts again? So I'll put a 1 there as well, and I'll make that my v dash, and I'll make this thing here my u. So v dash, so I'll start with u. U equals cos of ln of x, which means u dash equals cosine goes to minus sine, and then you multiply by the derivative of the argument. So then v dash equals 1, v equals x. This becomes, damn, I've been doing too much writing. My arm's hurting. My hand is hurting. uv, so it's going to be x cos ln of x minus v u dash. So v u dash is minus 1 on x, minus x times 1 on x sine of ln of x dx. Okay, this is bled into my work. Perfect. Again, x sine that cancels with that. That cancels with that, makes it a plus. So then now let's just expand. This minus expands to both of these and becomes minus x cosine ln of x, and then minus the integral of sine x ln of x dx. Wow, isn't that my OG integral? Yes. So it seems like, let's just let this equal I, do that in red. It seems like our original integral, which was the integral of sine, not sine x, sine of ln x, is equal to x sine ln x minus x cos ln x minus the integral. And then moving it over, you get 2 of these integrals. And then divided by 2. And there you go. So that one is the one where you have what we call recurrence, right? So it shows up again. Perfect. And then one more. Okay. So it seems like we're going to be letting this equal to, oh, actually, no. I just jumped to a conclusion. We're going to be letting that equal to u because I can differentiate it. I can't integrate it. And we'll let this equal to the v dash. So u equals ln of 2x. The derivative of that is just 1 on x. Because it's over the original times by the derivative of the inside. So then those 2's cancel anyway. V dash equals x squared, which means v equals a third of x cubed. So this becomes uv minus the integral of vu dash from 1 to 2, 1 to 2. So subbing in everything we know, we have a third of x cubed ln of 2x from 1 to 2 minus, and then I could take that third out already. V is x cubed times u dash is 1 on x dx, like this. Subbing in, we have a third of 2 cubed ln of 4 minus a third of 1 cubed ln of 2. Yep. And then minus a third of, this just becomes x squared, doesn't it? And then the integral of x squared is a third of x cubed. Like that. Okay. That's 8 over 3 ln 4 minus a third of ln 2 minus a third, and then this is 2 cubed on 3, which is 8 on 3, and then minus 1 on 3. Oh, geez, this is too much work to be honest. 8 on 3, ln of 4, minus a third of ln 2. And then expanding this out, first of all, 8 on 3 minus a third, quite easy, is 7 on 3. And then multiplying by minus a third, 7 over 9. Now, is there a way to simplify this? Probably. If you put it all as base 2, so let's make this 2 squared and then take that 2 down to the front. You're going to get 16 on 3 ln 2 minus a third of ln 2 minus 7 over 9. And then that gives you 15 over 3 ln 2. But then 15 over 3 is just 5. So 5 ln 2 minus 7 over 9. Let's go. Okay, we're done with integration by parts. Have a go at the exercise. I'll chuck it into the spreadsheet. I hope that helps. Stop recording.